When an object travels around a curve, something interesting happens. In the picture shown below, we have a car headed for a turn to the left with velocity v. If we imagine the road is icy, the car is not going to be able to turn to the left and will instead slide off the edge of the road to the right. Somebody riding in the car might say centrifugal force pulled the car off the road. If you're outside the car, though, you would probably just recognize that Newton's first law says an object moving with a particular velocity will continue to move with that velocity, both magnitude and direction, if it's not acted on by an external force. If the road is very icy, we have essentially no frictional force to act on it, so the car just continues in a straight line. Really, there's no such thing as centrifugal force. In centrifugal, the F there, you can think of this as fleeing. It's leaving the center of curvature. So the center of curvature for this road is over here at the lower left. The outward direction is this way, and that's the way this centrifugal force would act if it existed. If we're using Newton's laws in an inertial frame, we never have to worry about that. So if we were sort of in the helicopter looking down on this, watching it happen, we wouldn't have to worry about centrifugal force. However, if we want to answer problems like this, answer questions like this, and do problems from inside the car, then we might find it useful to introduce this fictitious force. This is also called an inertial force, because remember, it's really inertia that's taking the car off the road. Centrifugal force is one kind of inertial force, and another kind is the Coriolis force. That's what helps determine which way a hurricane rotates in the northern hemisphere versus the southern hemisphere. If we're in the inertial frame, if the car actually made it around the curve, we'd say there has to be some force present to provide a centripetal, and that means center-seeking, acceleration, since we see the direction of the velocity vector changes. Here we have the velocity vector in blue pointing straight up. Here at this point in green, it's pointing to the upper left, and that change in velocity means the acceleration had to go towards the lower left here. That's towards the center of the curve. That had to exist for the velocity vector to change like that. The magnitude, by the way, does not necessarily have to change. We could have a constant speed. You can set your cruise control in your car and go around a curve, and you will accelerate. If the velocity is constantly turning to the left, we see that the acceleration has to be radially inward, and that's where the center-seeking name comes from. Newton figured out that if you go around a circle, if you want to successfully make it through a circular curve, the velocity has to change in a particular way, and that is v squared will have to equal r times this centripetal acceleration, where r is the radius of the circle. From the outside, if the car is at the bottom of the figure, we would say, okay, the forces in the x direction, max, have to equal negative mv squared over r for a successful trip through the circle. The negative comes from the fact that we're turning to the left. The frictional force, and we don't know that it's Fs max, we don't know if the car is just about to break free or if this is, a slow turn on a dry road. The frictional force Fs is unknown, but we do know it must point to the left. It's the only force in the x direction, so we have negative Fs equals negative mv squared over r. We can say do the problem in the sense that we're not using a fictitious force. If we successfully make it through a circular curve, that means the acceleration is v squared over r by definition. However, even though centrifugal force is not a real force, it can still be a useful mathematical technique. If we put ourselves in the car's reference frame, what does it look like if we successfully make it through the curve? We would say if you stayed in your lane the entire time, that's kind of the definition of successfully making it through the curve. As far as you're concerned, your acceleration parallel to the ground was zero since you never moved from the right lane to the left lane or vice versa. So in this frame, we'd have a centrifugal force trying to pull us off the road, and it would be fighting friction, which is still acting in the negative x direction. So what we would have, just like Newton's second law always says, sum of the forces is max. We have this frictional force in the left direction, this centrifugal force in the right direction, and together they have to equal zero since we never changed lanes, so we know we had no acceleration. However, the formula for centrifugal force looks familiar. It's mv squared over r. So what we get out of this is exactly what we got from the other way of doing things, the centripetal approach. With the centripetal approach, Successfully getting around the curve would mean the acceleration is v squared over r towards the center, and there's no such thing as centrifugal force. In the centrifugal method, success means zero acceleration, and mv squared over r is a force directed away from the center. So if you think about it, we can either put the v squared over r, make it negative, and put it on the right-hand side next to an m, or we can have mv squared over r positive on the left-hand side. We get exactly the same end result. The only way we can screw this up is if we try to do both of these. So if we try to use the centripetal method and then throw in a centrifugal force, that of course will not work. As an example, let's say you're in a carnival ride, kind of like a Ferris wheel turned on its side. The idea is it rotates around a vertical axis and it pins you against the wall, and then the floor can drop out from under you and you're still safe because you're stuck against the wall by this centrifugal force that doesn't really exist. Let's say the wheel has a radius of 7.5 meters and turns at 0.3 revolutions per second. How sticky do the walls need to be? What value of μs do we need to keep you stuck to the wall? If we do this with the centripetal approach, we look at the forces we have. We have mg trying to pull you down into the gears. We have frictional force, which has to oppose that. And the normal force, which is the wall, as far as you're concerned, pushing you towards the center. Here we, of course, don't have a centrifugal force since we're doing the centripetal method for this problem. The normal force is sideways because the wall is there and it's always normal to the surface. Here we're going to have Fs max instead of Fs because we're looking for the minimum μs that will do the job, and that means we get the most friction out of it possible. So in the y direction, we better have Ay equals 0 because we know you're not going to fly out up and over, and if you slide down, that's going to be the end of you. So we have to have Ay equals 0. We look at the forces, we get Fs max equals mg. In the x direction, we only have the normal force, which is n, and it points to the left. We know that Ax has to equal v squared over r in the centripetal method if you make it through this curve alive. N points left, Ax points left, they're both negative. We have this. Now that we have a formula for normal force, we can use the formula for Fs max. If we didn't happen to know that the frictional force was at its maximum, we couldn't do this, of course. You have to be careful with that. So from the y direction, Fs max equals mg. From the definition of maximum frictional force, we have that equal to μs n. Then we plug in the normal force that we just found from forces in the x direction. We get this, we cancel the masses, and we get that μs is g times r over v squared. If the wheel is making 0.3 revolutions per second, circumference is 2 pi r, the velocity at the edge, and that's where we've assumed you are, 14.1 meters per second, so we would get μs as 0.37. No real ride is going to work like this, of course, because somebody could get on with a very slippery, with some kind of very slippery clothing and actually slide through, or the thing could stop suddenly and drop you to the center. Anyway, let's try the centrifugal method on the next problem. Let's say we want to go around a flat curve, 75 meters in radius, on a racetrack, and we have tires that have μs equals 0.85. This is decent car tires. How fast can you go before you slide off and crash? Notice, you may have to take my word for this, but we're going to have to use μs rather than μk here, because even though the wheels are moving, they're not sliding sideways, and in a few chapters we'll look at this in greater detail. If we look at the free body diagram, if we're using centrifugal force, we've got friction pulling to the left, trying to hold you on the road, centrifugal force trying to throw you off, mg and normal force. We still have no acceleration in the y direction since the car is not going to dig into the road or fly, so we get n equals mg, not very surprising on flat ground. The x direction, if we're using the centrifugal approach and we successfully get through the curve, Ax equals 0. So we put in our forces, friction, and centrifugal force. We know what the normal force is here, and we know that since it's maximum static friction, we can replace that with μs times n. And what we get here is our maximum velocity square root of μs gr